Next, we will consider a new topology of water distribution systems. Take note to the new location of both controllable and uncontrollable power switches. As similar to the previous systems, the utility tanks can generate up to 40 meter cubics of water only. Nonetheless, consumer A and B requires a higher volume of water, which are 100 and 70 meter cubics respectively. Thus, this system must perform the step-up function to meet the consumer's demand. When switch A and B are turned on, we can see the water generated tanks are generating the additional volume of water to accommodate the consumer's demand. At this moment, water will flow between the utility tank to the water generated tank only. Thus, we can say that these systems are executing the boosting function. Therefore, in the DC converter circuit, the inductor is called the boost inductor. To perform the boost function, the inductor must solely be connected to the DC supply. Hence, the load must be disconnected from the source. Once the water generated tanks completed their function, switch A and B are turned off and automatically the uncontrollable switches are turned on to connect the consumer tanks to the systems. At this moment, there is a direct water flow between the utility, water generated, and consumer tanks. Thus, in the DC converter circuit, the connection between the DC supply, boost inductor, and resistor is established when the transistor is turned off. Now, based on your observation, which switch should be on longer to generate water in the second water tank? Once again, the answer is A. Because based on the demand, the turn-on time of switch A should be longer than switch B. Eventually, we can see that the duty cycle is directly proportional to the demand. Lastly, let's consider the voltage equation of the boost converter. If Vs is equal to 40 volt and we apply duty cycles of 0.6 and 0.3 respectively, based on the output voltage values, we can verify that the output voltage is directly proportional to the duty cycle as well.